As the technology of man in space was developing, it became more and more apparent that our knowledge of the moon's surface as a possible landing site was not sufficient. To land man safely on the moon and get him safely off again, we had to know whether we could set up a precise enough trajectory to reach the moon. Could we design and build a spacecraft to land gently on the moon? Among all those lunar craters, could we find a place clear and level enough for a safe landing site? To make it possible for a man to land in the Apollo zone on the moon, better pictures were needed than those taken through Earth's best telescopes. In fact, better pictures might do more than find a landing site for Apollo. Scientists hoped they might resolve questions unanswered in the 300 years since Copernicus prompted Galileo to study the moon.
Surveyor was conceived to answer such vital questions as well as to survey possible target sites for the forthcoming Apollo manned landings. Hughes Aircraft Corporation was selected to develop the spacecraft under the overall project management of the Jet Propulsion Laboratory, California Institute of Technology. The launch vehicle system is a new, more powerful booster combination, the Atlas-Centaur. A basic triangular frame supports such vital components as the flight attitude controls, including star and sun sensors and reaction jets, which combine to make Surveyor a stable platform in space. The solar panel pointed at the sun can collect solar energy for conversion into electrical power. Flight communication with Earth is maintained through either of two omnidirectional low-gain antennas, telecommunications electronics, auxiliary battery, high-pressure gas and fuel tanks. Radar serves to mark the altitude above the lunar surface. The main retro rocket to slow the spacecraft as it makes its lunar approach. 3 vernier engines are designed to correct the flight path and later, coupled with a radar altimeter and velocity sensing system, keeps the craft stable and reduced touchdown speed to 8 miles per hour. Once landed, the high-gain antenna pointed back at Earth will return lunar photographs taken by the television camera. The camera, remotely controlled with adjustable exposure and focus and equipped with 3 color filters, will provide the first lunar surface color pictures. All elements of Surveyor were thoroughly tested. Drop tests verified design integrity, structural strength, and stability. Retro-rocket engine firings verified ignition system design, case strength, thrust level, and reliability. Shake testing duplicated acceleration vibrations to be encountered during liftoff, booster thrust, separation, mid-course maneuver, and terminal descent. Test results were thoroughly analyzed, then design changes, more testing, and re-evaluations. Liquid fuel engines in the vernier propulsion system were fired and refired in man-made environments to simulate the stringent conditions of flight into space. Then it was time to exercise Surveyor through in-flight sequences. A space simulation chamber duplicated the vacuum of space, the heat of the sun, and the deep cold of the lunar night. Final camera tests. The television system, precise for photomosaic work, is designed to produce pictures having a resolution 1 million times finer than the best Earth-based photographs. Now, the last and most important test. A Surveyor moon gravity model was balloon lifted and cut loose. Milestone, a completely automatic, fully controlled, rocket-powered soft landing. On board, velocity and altitude sensing radars, analog computer, autopilot, and throttleable rocket engines all tied together for the first time into a successful terminal descent system.
This is Surveyor 1, first of the spacecraft assigned to land on the moon.
At 1 a.m. Eastern Standard Time on the 26th of May, Surveyor 1 entered its protective housing.
Before a space mission launch, the Atlas, Centaur, and Surveyor come together for the first time at NASA's Combined Systems Test Facility in San Diego. Hughes Aircraft builds the Surveyor, and a crew from its Culver City plant followed the spacecraft to San Diego to perform a systems readiness test. Combining of all stages which make up a space mission ensures early confidence in the interaction of all systems. This was theoretically the first moon flight, only simulated and without propellants. Surveyor will be mated twice more at Cape Kennedy before the flight.
Surveyor arrives encapsulated in its nose fairing at Launch Complex 36A to be raised by the gantry crane and mated to the readied Atlas-Centaur launch vehicle. During the last hour of countdown, the gantry is withdrawn.
Memorial Day, 30 May 1966. At Complex 36A, the Atlas rocket has passed its final checkout. The Centaur upper stage is go. The shrouded Surveyor 1 is ready. Tracking and telemetry antennas at 15 stations around the Earth swing into their contact positions. Newsmen and television crews are standing by at key posts, ready to broadcast the results of Mission A, good or bad, to the waiting world. The control post is 2,300 airline miles west of the launch point, at the Jet Propulsion Laboratory in Pasadena, California. Here, scientists, engineers, and technicians stand by to assume command of the spacecraft after launch. Nearby, Von Karman Auditorium is reserved for members of the press. Even though the climax of Mission A is days away, a few have braved the early hour to be on hand from the start.
Cape Kennedy, Florida, Memorial Day, 1966. The scheduled date for the final performance of Atlas 290D and Centaur 1D. To intersect its target on the moon, Surveyor SC-1 must lift from the pad within an aperture in time between 9:40 and 10:27 a.m. Eastern Standard Time.
Minus 75 seconds. Steering Centaur lock stopping.
This is Surveyor Launch Control, T-minus 60 seconds and counting. T-minus 60, all still going well. We have secured the liquid hydrogen tanking on the Centaur's second stage. We're now at full fuel supply as far as the fuel of the Centaur stage. This is Surveyor Launch Control, T-minus 35 seconds and counting, all still going well. We're about to go through another final status check.
Minus 30 seconds. Status propellant. Go Atlas. Go Centaur. Go Centaur. Pressurization. Go Atlas. Go
This is
Centaur.
Surveyor Launch Control, T-minus 20 seconds and counting. Our status checks continue. They're all go at this point. T-minus 15 seconds and counting. The recorders on the strip charts are at a fast speed. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have ignition. We have liftoff. Liftoff at 41 minutes past the hour. Charts are starting here at the Mission Control Center and the start. The roll program is in and the pitch program is in as we switch to a flight azimuth of 102 degrees. Our charts are right on normal here during the early phases of the flight. Now 33 seconds into the mission, we are looking good. Surveyor Launch Control, 50 seconds into the flight. All systems still looking good during this early phase of the powered flight.
Launch time was 9:41, 1 minute into the time aperture. Atlas rolled from its launch pad heading of 105 degrees to a flight azimuth of 102.285 degrees, then began its pitchover into the trajectory. All powered flight events were close to nominal. Atlas, Centaur, Surveyor 1 was to become a storybook mission with a smooth transition through every step.
Surveyor Launch Control, now 2 minutes into the mission. All systems are still go at this time. Our tracking charts here in the control center very, very close to nominal at this point.
The first critical event is staging of the Atlas booster section at T plus 142 seconds.
This is Surveyor Launch Control, now 2 minutes, 25 seconds into the flight. We have confirmation of booster engine cutoff of the Atlas first stage, and the boosters have been jettisoned from the vehicle. The sustainer engine continues to burn on the Atlas vehicle at this point, and will burn for about 1 minute and 14 seconds longer after the booster jettison.
The insulation panels which enclose the Centaur stage jettison at 175.8 seconds.
This is Surveyor Launch Control, now 3 minutes into the flight. We now have confirmation that the insulation panels that surround the Centaur stage during the early portion of the flight have been jettisoned.
27 seconds later,
This is Surveyor Launch Control. We now have confirmation that that 2,000-pound nose fairing that protects the Surveyor spacecraft has been jettisoned. It appears to be normal. The time appears to be normal of the jettisoning of the nose fairing. This is Surveyor Launch Control. We have confirmation of sustainer...
at 239.4 seconds, the Atlas burned out, and the hydrogen-fueled Centaur separated clean.
This is Surveyor Launch Control. We have a confirmation of separation of the Atlas vehicle. We did not receive a VECO cutoff. However, with the separation, we now have confirmation also with VECO. Sustainer engine cutoff, vernier engine cutoff. The Atlas has separated, and we can confirm the Centaur stage has ignited. Those two 15,000-pound thrust engines have ignited. We are continuing on the flight, all looking well at 4 minutes and 40 seconds into the flight.
This is Surveyor Operations. We're now launched plus 9 minutes and 8, 9, 10 seconds. Everything still looks good. Centaur still burning. This is Surveyor Operations. The ship Arnold, the uprange tracking ship, is in track and is tracking the spacecraft at present. There is a voice report in from Antigua that they have observed the cutoff of the Centaur engines.
Centaur's main engine burned for 7 minutes and 18 seconds, and then shut down when the vehicle reached injection velocity. Surveyor separated from its mounting 68 seconds later.
This is Surveyor Operations. Ascension Island reports that they saw the initiation of Centaur retro.
Centaur's final maneuver was a turnabout in space. Hydrogen peroxide jets added a vertical vector to put Centaur out of a direct line with the spacecraft. Unused propellants gassed out in the direction of flight to widen the gap between the vehicle and spacecraft.
The electrical disconnect, high power is on the antenna has extended. All things look nominal. The Surveyor apparently is free and operating. Standard data form is now being received here in Pasadena from Station 51, which is at Johannesburg.
As the spacecraft reached a point over South Africa, its flight was more directly away from Earth. Earth's rotational speed overtook the horizontal velocity of the spacecraft, and from the Earth, it appeared to reverse its direction, now apparently moving from east to west.
After launch, control of the mission passed to the NASA Center in Pasadena, California.
Here, during the early hours of flight, scientists, engineers, and computers churned through the data.
Surveyor locked onto the sun and the star Canopus and was stabilized in cruise mode.
Five hours later, the distance between Surveyor and Centaur was 1,054 kilometers, about 3 times greater than the required 336 kilometers.
By launch plus 15 hours, the flight path was analyzed. Surveyor would land in the target area, but it was decided to refine the path.
The mission director has exercised an option. He has decided to land Surveyor about 1 degree north of the original target.
The precise aiming point that's now been picked has the coordinates on the moon of 2.32 degrees south latitude. I repeat, 2.32 degrees south latitude, and the longitude is 43.83 degrees west. I repeat, 43.83 degrees west.
The correction command was sent to Goldstone. From Goldstone, the order went out to roll and pitch Surveyor into a new heading and fire the vernier engines for exactly 20.8 seconds.
The station now reports it has completed all of the preparations for the thrust maneuver and is now waiting for the next command to execute the mid-course thrust. That will be in 20 seconds from now. The station will send that command at that time. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, mark. Telemetry confirmed. Ignition is confirmed by telemetry. We're now in the thrust phase of the mid-course maneuver. We notice a change in Doppler in accordance with what's expected. Very clear signal. Shut-off has been commanded, and engine shut-off has occurred.
A critical maneuver accomplished, Surveyor, on corrected course, was commanded back into cruise mode.
Left to right, Mr. Robert J. Park, the Surveyor project manager here at JPL, and Dr. Benjamin Milwitzki, the Surveyor program manager at NASA headquarters in Washington.
As of right now, the Surveyor mission is about 28 hours long, and the performance of all systems up to date has really been exceptional. For example, the launch vehicle. As you know, Atlas-Centaur is a comparatively new launch vehicle combination, and its performance has been flawless for this mission. The injection has been very, very close, with a very small miss from the intended aiming point. The Lewis Research Center of NASA and General Dynamics Comdat really deserve all kinds of congratulations for the wonderful performance of the vehicle. The spacecraft has behaved excellently up to date.
The press conference in Pasadena also reached assembled newsmen at Cape Kennedy and at the NASA Center in Houston. People of the free world were represented in best.
Tom Franklin, KTTV. Will the pictures sent back be motion pictures or stills?
They'll be stills, in the sense that the camera takes one picture and then transmits it back over a period of seconds.
Cape Kennedy, we're now ready for questions from down there.
Could you give us a distance in miles that you expect the spacecraft to land from some fairly large geographical point on the moon, such as a large crater?
We're landing just essentially north, a little bit slightly north-northeast of the crater Flamsteed. Speed. It's about 60 kilometers.
Long hours pass. The Deep Space Network continues to command, monitor, and report on the flight.
In the late afternoon of June 1st, 1966, as the Earth turns east at 1,000 miles per hour, the big dish at Goldstone, California swings to the horizon, to the point where the moon and Surveyor will rise. At JPL, Mission Control readies itself for the final maneuver, touchdown, and photo mission.
Through terminal maneuver preparations, events are precisely as planned. Surveyor velocity is about 4,654 miles per hour. Altitude is about 1,000 miles above the moon. Velocity increasing. Distance closing. Surveyor has been turned into its landing attitude.
In a short time, the major television networks will broadcast the Surveyor landing, exactly as it happened. From small vans, the signals will pass to microwave antennas, and on, into millions of American homes across the land, and by satellite to Europe.
10 seconds. Waiting for the marking radar. 4, 3, 2, 1. Mark. We should now get verification of the marking signal. AM on mark.
We are now turning on the thermal controls for the fuel tank vernier line, tank number 2. Then the oxidizer tank 2, lines 1, vernier lines 1, oxidizer tank 2, thermal control power is off. Vernier lines 3, oxidizer tank 3, thermal control power off. Power is off on the vernier lines for tanks 1, 2, and 3.
I'd like to ask Mr. Park to make some remark.
They then waited until the time to turn on the altitude marking radar, which, of course, is a device which was going to trigger the final sequence of events. This was turned on precisely at the scheduled time, and it marked at the time we expected it to.
Now 1 minute and 30 seconds away from expected retroignition. 30 seconds to go. 20 seconds to go before we expect the marking radar to turn on, to send its mark. 10 seconds, waiting for the marking radar. 4, 3, 2, 1, mark. We should now get verification of the marking signal. AMR mark. Vernier ignition, retro is now firing. Ignition looks stable. Stable ignition. We are now at 5,148 miles an hour. Down to 116,000 feet, 4590.
This started the terminal sequence. We soon got confirmation that the retro motor had ignited and was slowing the spacecraft down, that the spacecraft was stable.
8 G's acceleration. We are now at 30,000 feet. Retro burnout is confirmed. 32,000 feet.
After the retro burned out, we got confirmation that the radar altitude and Doppler velocity sensor had in fact locked onto the lunar surface and was giving its altitude and velocity measurements and was controlling the spacecraft properly down its sequences. It approached the moon in essentially a standard fashion and settled on the surface in a fairly soft fashion.
10,000 feet. All signals are normal. 8,000 feet. 250 feet per second. 8,000 feet. 200 feet per second. Surveyors reported in excellent condition. All signals look good. 4,000 feet, stable. 4,000 feet and stable. 1,000 foot mark. 800 feet, 600 feet. 400 feet. 200 feet. 100 feet per second. 100 feet. 100 feet. 13 feet per second speed.
Cue touch. The bus chief reports a touchdown. Signal strength is reported at minus 125.5 dBm. We'll now await further indication on the condition of the Surveyor.
The indications from the gyros were that it had landed on a very level spot. They indicated that it was essentially not very far off the horizontal, maybe just a few degrees. A series of interrogations of the spacecraft was then made and indicated that all of the spacecraft was operating properly. During the same period of time, certain elements that were no longer needed on the lunar surface were turned off in order to conserve the power.
11 hours, 17 minutes, 37 seconds Pacific Daylight Time. The station, the Goldstone station, has just now been commanded to reconfigure its setup to receive the 200-line picture data. The station has reported itself ready to receive 200-line television. And the command link between the operations area here in Pasadena and the Goldstone site has now been turned over to the Space Science Chief, Jack Lindsley, who will now direct the commands for the first television picture. He is now directing the station to turn on the camera power. That has been sent. Camera power command on has been transmitted. The camera is now warming up. We are standing by for the start frame command. We are receiving a picture. Video is being received. The picture is now coming through.
We then set up to prepare for and accomplished the first picture of the landing line, as planned.
Extremely clear picture of the pad on the spacecraft. We are receiving the second picture. It's now coming through. This is the surface of the moon, and on one of the Omni antennas in view.
We then further took measurements to determine the fact that we could move the solar panel and the high-gain antenna to their proper positions. We then went into a planned sequence of pictures with the 200-line mode, and everything worked perfectly during that time. We then erected both the solar panel to its proper position to provide power to the spacecraft so that it can operate essentially without concern about depleting the battery, and then pointed the high-gain antenna back at Earth, and then proceeded to take a series of pictures on the 600-line mode, interspersed with interrogations of the spacecraft to determine what its conditions were. The temperature of the spacecraft had been acting very close to what we expected once we were on the lunar surface.
Switching to 600-line television, the camera later looked down at landing leg number 2, at the depression and deformation of the surface caused by the landing impact. Moving up toward the horizon, the camera discovered some small rocks scattered about a small crater.
From the keyboard, Internet 1120. 1100 mark.
This picture of the moon's horizon is tilted, showing the angle at which the camera sits. The bright circles are reflections from the sun, which is just out of view.
1100 mark.
A composite of two narrow-angle pictures shows the crest of a small mountain range about 12 miles away. The bottom part of the mountain is below the horizon, which is less than a mile away. This small mountain is part of the rim of an ancient, nearly buried crater, which is over 60 miles in diameter. Surveyor 1 landed inside the rim.
I think the general thing that we see from these pictures so far is that the surface around our landing point is generally level. There are a number of objects in the photograph which certainly appear to be rocks and boulders, fragments of rocks scattered all over the lunar surface from very close to the spacecraft to as far as we can see.
As a result of this very fine flight, and I must add, I don't expect to see anything like this again happen in my lifetime. It puts us ahead, I feel, approximately 1 year with regard to the current Surveyor program.
Mr. Park, can we hope to see man's first view of the Earth from the moon, and if so, when?
Well, I got some bad news. These three maneuvers I indicated earlier were required because of the antenna problem, which incidentally put us in a very good position lighting-wise for taking all these pictures you've seen. Also put us in a position where we cannot raise the camera high enough to look at the Earth.
Last question. Is there any indication that the vernier engine exhaust impinged on the moon or affected the surface in any way?
You haven't seen anything in the pictures?
No, we haven't looked specifically to that. We didn't notice.
That's the only way we'd get any indication on it. They were cut off, as you know, at the altitude where we were trying to avoid any disturbance in the surface of any significant degree.
Thank you very much, gentlemen.
Individual scenes were arranged to form a lunar surface mosaic within the shell of a lunar model. Pictures of a Surveyor footpad show only light surface indentation. At the landing site, measured surface strength 6 to 10 pounds per square inch. The lunar surface texture, not thick layers of loose dust into which spacecraft or men could sink, but separate, very fine granular particles weakly held together. Detailed color measurements show the lunar surface material uniformly gray. There are open areas, craters, and many rocks, some a yard or more in diameter. Overall conclusions of great significance to the Apollo project. In the area of the ocean of storms, man can land and walk on the lunar surface. As the mission continued, Earth days passed and the sun set on the lunar plains. The deep, cold space night set in.
During its active life, Surveyor transmitted 10,338 pictures over the 12 Earth day period of operation.
Soon the moon's shadow will envelop it, and temperatures will drop to 260 degrees below zero Fahrenheit.
Surveyor went into a frozen sleep. It was expected that the frigid 260 degrees below zero would put electronic systems out of commission, but they survived to transmit again for a short time.
But 21 Earth days later, in the noon of a new lunar day, Surveyor came back to life. January 1967. 220 days after landing, commands were sent, and the spacecraft still responded, though the mission was officially over when Surveyor was commanded to hoist high its antenna and solar panels, to cast forever its long shadow across the lunar mare, a landmark for future missions.
Future flights will photograph other possible manned landing areas and carry instruments to measure surface hardness, information needed before men land there.